All right, in this video, I'm going to talk about k-means clustering algorithm. But before I start, I have to give you an overview of unsupervised machine learning algorithms because k-means clustering algorithm is a member of the unsupervised machine learning algorithms. If you remember, so far we've been discussing supervised machine learning algorithms in which the training data set has labels, right? There is a true outcome for, or a true classification for every observation in the data set. And when we design a machine learning algorithm, our objective is to figure out the relationship between the set of features and that particular outcome or those particular labels, right? So that we can accurately predict the future labels based on different features in our data set for testing or when you're actually implementing the machine learning algorithm in real life. The important thing here is that there is always a Y data set, or there's always a labels data set. There's always a ground truth, and our whole purpose is to get as close as we can towards that ground truth. Whereas in unsupervised machine learnings, the training data does not have labels, meaning that there is no true outcome. And any machine learning algorithm that we're designing is only to figure out the relationships between the features only. So there is no ground truth to get close to. Now, there are multiple examples for when you would implement an unsupervised machine learning algorithm. A very famous one is when you want to decrease the dimensions in your data set. Basically, when you want to reduce the number of features. You may be thinking, isn't the more data the merrier? Not necessarily. As I will discuss in the next video, dimensionality can be a curse and can actually reduce the accuracy and other performance measures of your machine learning algorithm. And principal component analysis, as a particular example of unsupervised machine learning algorithms, in this case, could help you a lot by reducing the dimensions. Another very famous example, which we're going to do here, is clustering, which basically you want to group similar observations together within the same cluster. Again, here, you don't have a particular group number or label for each observation. You just have the features. And what you want to do is to see if you can group these observations so that the ones that are more similar based on their features are going to be grouped together. And another example is anomaly detection. So if you could run an unsupervised machine learning algorithm that looks at the features of a whole bunch of observations and figure out what is normal, then you can see if a new observation falls within the range of those normal features or not. And if it doesn't, then it could be categorized as an anomaly. Here is a picture that would help us start our discussion about k-means clustering. If I showed you this image, you would be able to say that, all right, it seems like there are different segments in this picture, like these green segments in the forefront, and then you have these beautiful colored flowers here, and then there is this brownish segment in between, then you have another colorful segment here, and then the rest are green, probably a different shade of green. So you could say there's 1, 2, 3, 4, and probably 5 segments in this image. How are we going to be able to ask a computer to do that for us? Well, in the next video, I'm going to show you how to implement that exact idea in Python. But before I do that, I want to talk about the k-means clustering algorithm, and more importantly, talk about the difference between classification and clustering. So far, we've discussed a lot about classification. Basically, most of the models that we've covered in these videos are about classification. A very famous example was when we wanted to classify iris flowers into different classes of setosa, versicolor, and virginica. There, we had a bunch of features. In this plot, I'm only showing the two features of petal length and width, that we could create a scatter plot. And the important thing is that every single observation had a particular label on it, right? We knew that this one, for example, is setosa, and this one is virginica. Whereas in clustering, we use the exact same data set. The difference is there is no label on top of each observation. So to computer, they all look the same. And the task is to see if we can use these features to recreate these classes. So based on these two features on the screen, the computer would be very easily able to say, all right, these are in the same cluster and these are in another cluster. In other words, it seems like the clusters for virginica and versicolor would be grouped together because it's not that easy to separate them. However, remember, we have more than two features. There are actually four features of sepal length and width plus petal length and width. And if we add those features, then computer will be able to easily separate the observations in these groups as well and come up with three clusters that we have. Now, going back to the very first point that I made about the fact that there is no true ground truth about unsupervised machine learning algorithms, somebody will say, oh, you know what? I'm going to cluster all of these into one cluster and say that these are all different features, different types of the same type of plant, which is iris. So I'm going to say this is one cluster sample of iris. Well, that would have been correct, right? Another person may say that, no, I want to go ahead and break it down to three groups of setosa, versicolor, and virginica. That would have also been correct. Which one is going to be preferred? It depends on the data set that you have. In addition to that, there are some statistical approaches that you could use in order to figure out the appropriate number of clusters. We are going to discuss that as well. The point is, there is no definite answer to determine whether something is correct or not when it comes to unsupervised machine learning algorithms, including clustering. Now, one of the very famous clustering approaches is called k-means clustering algorithm that was introduced in the early 1980s. And this is how it works. Suppose that you have a sample of observations, that would be your training data set, and each observation has two features, x1 and x2. Using x1 and x2, you can create a scatter plot, and this is how your data set looks on a scatter plot. There's a bunch of observations spread out on a two-dimensional plane. Now, assume that we decide to cluster these observations into 5 clusters. This means that we determine the value of k to be equal to 5, right? So that is where the k-means come from, means that we want to have k clusters. Who decides about the number of clusters? Again, as I said, in large, it depends on the context and the data that you're working with. Also, there are some statistical approaches that you can implement in order to help you determine the correct number of k. Assume that we decide to have 5 clusters, all right? We randomly assign these 5 clusters on the plot. It doesn't matter where we choose them, right? So completely randomly, we start by 5 cluster centers, or as we call them, centroids. Once we randomly assign those centers, we're going to assign each observation to the center that is closest to that particular observation. So, for example, take this point, right? We calculate the distance between this point and every other centroid and see which one is closest. Obviously, this one is closer. Therefore, we are going to say that, all right, this particular observation belongs to this cluster, all right? And now I'm using color codes to distinguish between different clusters. Now, here is another example. This particular yellow observation, we calculate the distance between that observation and every one of those 5 randomly selected centroids and figure out the closest ones, which is obviously this one, and say that, all right, this observation belongs to this cluster, and for the ease of interpretation, I use color codes to identify them. So this is going to be in the cluster of yellow. Once we have done that, we can actually update the cluster centers so that they are going to be moved towards the real center of that particular cluster. So, for example, now that we have decided that these 5 points together represent the yellow cluster, we can obviously see that this yellow square is very far from the middle. So we have to move these yellow square somewhere in between so that the observations within that cluster would have the shortest possible distance to that particular centroid. That means that this yellow square would be moved to this point. So from here to here. And that happens for the other cluster centers as well. In this case, if you pay attention to how the orange center changes, you see that it slightly moves, all right? So it moves towards the center of that cluster. Now we have to update the membership to each cluster based on the new position of the centers. Remember, first, we had selected this place randomly to be the center of the yellow cluster. And based on that, you could say that, all right, this observation is very far from the yellow center, but is closer to the orange center, so I'm going to assign it to the orange cluster. However, once you have moved the center of the yellow cluster from this point to here, then this observation is no longer closer to the orange center, but it is now closer to the yellow center. So after we move the center of each cluster, we have to update the membership of the observations in each cluster. And as you can see here, some of the orange observations are now going to be assigned to the yellow observation, and so does the pink and red observations are going to be updated accordingly. So once we do that, we have to repeat step 3, right? And update the cluster centers again, because now the members have changed and the centers would change accordingly, because we want to move them to a position that is the closest in distance to all observations, right? So once we move these centers again, then we're going to reassign the cases again, following the same logic that, look, now that we have moved the yellow center to here, this particular orange observation is then going to be closer to the yellow center than the previous orange center, and therefore they have to be reassigned. And we repeat this process until we converge, meaning that we cannot move the center of the cluster to a better position. This is the best place that we can get, in the sense that it has the closest mean distance to all the other observations within the cluster. And we can no longer reassign any observations from another cluster to the new clusters. And that indicates the convergence. And in this particular example, here is the final status of the clustering algorithm, meaning that the algorithm has converged, right? With 5 clusters of observations for us. So the k-means algorithm is guaranteed to converge, right? It will always converge. However, it may not give us the best clusters, because remember, it starts with random assignment of cluster centers, right? So depending on how well those initially assigned cluster centers are chosen, the final result may be of different quality. So here is an example. Suppose that we have, again, two features and a bunch of observations. We plot them on a two-dimensional plot, and this is what we see. Now, visually inspecting, it seems that we have one group, two groups, three, four, and five groups or clusters here, right? And we can implement the k-means clustering algorithm, and it will give us something like this. So depending on how it has chosen the cluster centroids, you may have these 5 clusters, right? Seems reasonable, but it could also be like this, right? Maybe it chooses this as the cluster and it groups these two as one cluster and so forth, right? Or this. So how are we going to decide between these different possible clusters, right? Which of these options is the best way to go forward with? Meaning that even if we could determine that we need 5 clusters, still we may have different combination of 5 clusters as shown in this example. Well, one measure to go with is inertia. Inertia is basically a model performance metric that is defined as the mean squared distance between each observation and the closest centroid to it, right? And when we calculate the score of the k-means algorithm in scikit-learn in Python, we get the negative value of inertia. And it's because the scikit-learn wants to be consistent with other performance measures so that the larger the score is, the better it is. That's why it's multiplied by a negative. In order to comprehend what inertia is, think about what it is basically measuring. It is measuring the distance, the mean squared distance between each observation and the closest centroid to it, which means that in the extreme, if we say we had 5 observations and we clustered them into 5 groups, meaning that each observation is going to be one cluster, and that observation is going to represent its own centroid of the cluster, then inertia would be 0, right? Because there is 0 distance between each point and itself, right? That is the smallest inertia that we can have, right? And in these cases that we have more observations than clusters that we have, then inertia is going to basically start to grow. So how are we going to use this metric in order to improve clusters? Well, basically we can initiate the clusters centers at some good starting position and then run multiple classifications with random initial centroids and choose the one with the lowest inertia, right? Or the greatest score. So we are going to basically be able to compare these 3 possible clustering outcomes using their inertia and choose the one that has the lower inertia or the greater score, performance score in Python, as our best one. This is assuming that we have already decided on the number of the clusters that we want, right? So inertia is a good measure to compare the performance of, say, 2 clusters, two clustering results that both have the same number of clusters. However, if you want to compare the results of a clustering algorithm that creates 3 clusters with another one that creates 10 clusters, then inertia is not a good one because it always is going to prefer the one with the higher number of clusters, right? So one of the enhanced version of the k-means algorithm that we just discussed is called k-means++, that was introduced by these authors. And what it does is that it suggests a smarter way for choosing the initial centroids, right? In particular, it chooses the initial centroids so that they are as far from each other as possible. Again, remember, we said that depending on how you choose the centers, at the beginning, the performance is going to be different. So you have to figure out a smart way to choose them appropriately. And k-means plus plus is a particular algorithm that is going to ensure that those initial randomly chosen clusters, or no longer is basically random, are going to be appropriately chosen so that the chances of the algorithm getting good clusters for you is higher, right? And this is basically the default method in scikit-learn. You don't have to worry about it. And then there is another enhancement, which is called accelerated k-means, that uses the triangle inequality to avoid many unnecessary calculations so that the clustering runs faster. Okay, so it is, again, the default method in scikit-learn. The details are beyond the scope of these videos. I'm not going to go into them. Now, so as I discussed before, inertia is not a good performance measure because it keeps decreasing as we increase the number of clusters, right? To the extreme, it is going to lead you towards having the same number of clusters as observations, right? Because it wants to minimize the squared distance between observations and their centroids. So what are we going to do about it? If you want to figure out the appropriate number of clusters, then a good measure is going to be a silhouette score, which is the mean silhouette coefficient over all the observations. And here is basically how it is calculated. The silhouette coefficient is very simple. It's b minus a divided by max of a and b, in which a is the mean distance to other observations in the same cluster, and b is the mean distance to observations in the next nearest cluster. Note that this is for each observation, right? So you take any observation in your data set, or basically every observation in your data set, and you calculate the distance of that particular observation to all the other observations in the same cluster, okay? Take the average, that is going to be A. Then you take that observation and calculate its distance with every other observation in the next closest cluster. Take their average, that is going to be your B. The difference between B and A divided by the maximum of B and A is going to be the silhouette coefficient. Remember that this is only for one observation in your data set. You have to repeat this for every single observation in your data set, and you can imagine that it is very computationally expensive. That is why in the video that I'm going to show you, you would see that it takes quite a long time for the computer to be able to calculate the silhouette score. Ultimately, this is going to range between -1 and 1, which 1 means that the observation is inside its own cluster, and -1 means that the coefficient is not assigned correctly, right? So it's very similar to the correlation coefficient in the sense that 1 means that they're very highly correlated, and -1 means that they're highly but negatively correlated. So the higher it is, the better it is, right? So the number of clusters that give you the highest silhouette score is the best number of clusters. And you can basically implement the Python code to create various number of clusters, in this case k, starting from 2, 3, all the way to whatever the number you want. And then it calculates the silhouette score for each number of clusters. And then looking at the plot, you can choose the one that gives you the highest silhouette score, and afterwards it's going to decline, right? So here you can see that with k equal to 4, you get the highest silhouette score. Therefore, it is good reason to believe that in your data set, in this particular case, k equal to 4 or 4 cluster is the best case to go with. To see how we can implement k-means clustering, for image segmentation, make sure that you watch the video in the description.